Okay, you can go ahead now.
Okay. Hi, my name's Stephan Fitzpatrick. I'm a instructor of geology and environmental science here at Georgia Perimeter in Clarkston. I'm going to be talking about hydraulic fracturing today. Now, hydraulic fracturing could very well affect something like this. Hydraulic fracturing, no doubt heard a lot about in the news. It's a hot button topic. I'm going to try to explain it as objectively as possible. There are some clear benefits to hydraulic fracturing, so I'm not going to go over to the side of it's horrible, but I'm not going to go over to the side of, oh, it's the best thing since sliced bread, because to weigh the advantages, there are some possible impacts. In fact, there are impacts that have been recorded as data. So that's what I'm going to be talking about.
You need to advance the slide.
Oh, yeah. Well, yeah, that's okay. Slide, actually.
Oh, your presentations are on there? Okay.
Yeah.
Did you bring it?
No, did I?
Oh, yeah, okay.
Actually, I can run and go get it. I'm just across the.
I can download it on my computer, but that's okay. It's kind of a little bit confusing, since I'm running the Windows session from my laptop, and then, the speaker can use the desktop.
Yeah.
Because otherwise, you see the Windows frame around the presentation, and that eats up screen space.
Yeah, and this time I'm not going to be near the screen. I got to. Yeah, this actually looks very nicely here. Well, what I have here is a presentation, and the presentation is going to explain. I'm going to go into the history of fossil fuels. Because I thought that we needed to get some background. Unless you're taking a petroleum geology course or an economic geology course, you don't. It's kind of a topic that's kind of kept off to the side. But hopefully not after today. Yeah. I think sometimes it asks for the password. Sometimes it doesn't.
43 pages.
Yeah. Yeah. Well, not a huge topic.
All right. Yeah, this should be loading shortly.
I feel good with this room. This is a nice room. I kind of wish they'd give me this room.
Yeah,
I like this room. Yeah. No, the last one. That one was not. Well, yeah, not a lot of fun. Okay, and you just maybe, well, whatever you have to do. Yeah, slideshow would be awesome. Awesome. There you go. Okay. This is what I'm talking about. Fracturing truth using hydraulic fracturing for mining fossil fuels. Okay.
You still got to advance.
Oh, so I have to go over here.
Yes.
Okay, so I'm going to be going out of the field of vision.
That's fine. That's okay.
It's going to be kind of dynamic here.
Yeah.
A lot of action. Okay, hydraulic fracturing for fossil fuels. Okay, we utilize fossil fuels every day. Probably every one of us had to use a fossil fuel to get here. Unless you have an electric car, and even then, you, in a secondary manner, use a fossil fuel of some sort. Unless you were using nuclear energy, which we do get here. Fossil fuels are important in our daily life. They basically form the basis for our civilization. Hydraulic fracturing is a technique that enables us to obtain more oil and natural gas. Maybe we ought to turn that to me. I ought to stand here, or should I just go back and forth? Still doing choreography.
Yeah. Well, Well, we can try to do
The
that.
dance number.
Okay, yeah, let's just do that, and then I can, maybe put it over there.
Okay. Is that okay?
Sure.
And I will turn this around.
You'll be right with me.
I'll let you do, yeah, I'll be right with you. We're coming up with new. We don't want to lose our audience here.
Okay, here we go.
All right, hey, that looks
Okay.
great. Okay, fantastic. All right, so what are fossil fuels? Fossil fuels are combustible energy resources derived from the remains of ancient organisms. Very simple, okay? To turn these organisms into usable fuel sources takes an immense amount of geological time. Geological time, or geologic time, is measured in millions of years. Spans of time that we can't comprehend. Okay? They're transformed into deposits that contain high amounts of compounds that contain only hydrogen and carbon, otherwise known as hydrocarbons. Okay? You take both animals and plants and do this. But the animals that are commonly turned into fossil fuels are microorganisms. Okay. There is another type of fossil fuel that we'll talk about too. We're just going to briefly touch on it. Methane is the simplest hydrocarbon. Okay. CH4. All right. It occurs on Earth or in the Earth as in the gas phase. There is a solid type of methane known as the methane clathrate, which is an ice form of methane that is surrounded by a lattice of water ice. It occurs deep under the ocean, in substrate beneath the ocean. It also occurs in the Arctic and Antarctic. We're not going to talk about it. It's a potential fuel source, but not yet. There are enormous amounts of hydrocarbons in the Earth. Okay, and these hydrocarbons number over 100,000. Crude oil contains a great number of them. Crude oil isn't one type of hydrocarbon. It's a soup, it's a solution of many different types. Fossil fuels. Ready to start singing. Fossil fuel deposits are found in sedimentary rock layers. You find these things in sedimentary rock layers. If you put them through metamorphic processes, remember there's three types of rock, right? There's sedimentary, metamorphic, and igneous. Igneous melts everything. Everything volatilizes. You can't do it. Same with metamorphic. Metamorphic, intense heat and pressure. You cannot keep these things going. They'll volatilize. Okay. So in these sediments, otherwise known as strata, is where you're going to find your fossil fuel deposits at specific and discrete windows. You have to understand stratigraphy to understand the occurrence of fossil fuels, both in liquid form and in solid form. The two basic types of fossil fuels are, I combine oil and gas, the fluid, and coal, which is the solid form. Okay? They require very specific conditions underground. A very specific window for each type. Okay? The creation of sedimentary rock and sedimentary deposits is known as diagenesis. That's what it's known as. Again, you have to understand these processes in addition to other types of geological exploration, which I'll discuss later, to understand where to look. Coal. Okay, coal is a solid fossil fuel formed from ancient woody plant material. Most of it was formed in the coal swamps of the Pennsylvanian and the Mississippian 300 million years ago. Back then, there were conditions in which the earth was warmer and the earth was covered in growths, these growths of massive woody plants, okay, and coal swamps. Okay, as these things died, they were buried, and there's a continuous process of burial. You eventually ended up with coal, because as coal gets buried, oxygen's driven out. As the oxygen now you have the capacity to retain a lot of carbon. Okay? And that's how coal is formed, basically. Let's move on to the liquid portion. Okay? Oil and natural gas. In difference to coal, these organisms are slightly different. A lot of this stuff formed in what they call epicontinental seas. The middle part of the United States was part of an epicontinental sea, 100 million years ago. And in these epicontinental seas, you had a lot of microorganisms die, sink to the floor of the ocean, and get buried. Okay, and if you have low oxygen conditions in the right window of pressure and temperature, in time, you might end up liquefying the remains of these organisms into the soup we know as crude oil. These are ancient microorganisms. And this chart right here says 300 to 400 million years ago. That would put it, that'd be the beginning or somewhere in the middle of the Ordovician period. But a lot of this stuff also formed during the Mesozoic. Okay, so it's a continuous process. I mean, we have coal from the Mesozoic. We have coal from the Paleozoic. Paleozoic came before the Mesozoic. So you have three basic eras in our quote-unquote modern times. You have the Paleozoic, the Mesozoic, or the time of the dinosaurs, and the Cenozoic. We live in the Cenozoic. We live in the Cenozoic era right now. The age of a given oil deposit, as well as the temperature within the oil and pressure to a certain extent, is critical for formation. You have a window here. Anything outside of the shaded area, you're not going to have much going on. Here, you don't have enough time. Okay? Here is your sort of sweet spot. Here, it gets too hot. These things start to volatilize, meaning they turn to gas. Oil fades out, gas fades out. Okay. You have to somehow keep these things intact. Oil and gas originated at Terrigen. Okay? So once it started forming, you initially formed kerogen, which is a mix of organic chemical compounds. It's insoluble to other oils. It's kind of resistant. Okay? Some coal actually contains kerogen too, but only a small amount. And when heated to the right temperature under pressure and depth, kerogen releases petroleum and natural gas. It will do both. Petroleum and natural gas are somewhat related, although one's a gas and one's a liquid phase. Okay, so these rocks, such as shale, which has happened, are become known as source rock. Okay, source rock is where you find these deposits. It can be sandstone. It doesn't need to be shale. In fact, in early oil exploration and development, it was a lot of sandstone. Sandstone's porous. It made for oil fields and oil plays that became depleted, which is why we're starting to become dependent on this stuff, upon alternative sources. Liquids and gases are both considered to be fluids. Okay, when you start talking about liquids and gases in geology, you refer to fluids. Okay? So there's a solid that holds its shape, fixed volume. Liquids take the shape of the container, fixed volume, and they have a surface, of course, where they're not occupied by the container. Gas takes the shape of the container and the volume of the container. There's a big difference here. Liquids are heavier or denser. They're more affected by gravity. Okay. So in any formation, you're going to have water at the bottom, oil or petroleum above that, and at the top, you're going to have natural gas. Natural gas is extremely mobile because it's gas and it's highly energetic. What's the difference between oil and natural gas? Well, crude oil, is a liquid, and it contains many different hydrocarbons, a solution of many different hydrocarbons. Natural gas is simpler, basically methane. Okay? The simplest hydrocarbon. One thing that they all have in common is crude oil and methane, or natural gas, both represent pretty large amount of potential energy. Hydrocarbons in general contain more stored energy than many other types of compounds. This energy is held in the molecular bonds. It's called chemical potential energy. Okay? It's held in the bonds between carbon and hydrogen. It oxidizes. It reacts to oxygen. That's what happens with combustion. The formation of, let's say, when you combust natural gas, or CH4, you're going to combine it with oxygen, and the formation of those bonds is what releases energy. It's called an exothermic reaction. Okay, they're also fluids. It's important to understand that these are fluids. Okay, when fluids are introduced into a system, they go into equilibrium, or they attempt to go into equilibrium. Okay, this is dependent on the energy of the fluid and the pressure of the entire system, also known as partial pressure. For instance, when you let air out of a balloon, it disperses in the atmosphere until, theoretically, it all goes back into equilibrium. Liquids evaporate for much the same reason. Like acetone will evaporate very quickly. Not only is it a liquid, but it's also, its molecules tend to be very energetic versus, let's say, water. Okay. Remember, acetone's a good example, too, because what is acetone? Well, it's a petroleum fuel product. It's a petroleum product. A lot of what we have around us are petroleum products. Okay. Traps. This is where oil and gas stay underground. You have stratigraphic traps, fault traps, salt dye piers, and another type of stratigraphic trap. And what happens is you have impermeable cap rocks, often composed of either crystalline rock, what do I mean by crystalline rock? Metamorphic and igneous rock. Metamorphic and igneous rock tend to be much denser, impermeable rocks unless they're fractured. Or it could be some sort of clay stone. Clay has the property, when it's just clay, of being porous but not very permeable. And that's translated once it becomes a sedimentary rock. Most of the sedimentary rocks on the surface of the earth are shale, by the way, which is derived from clay deposits. Impermeable cap rock prevents the fluids, especially gas, natural gas, from migrating. Natural gas is incredibly mobile. Once you let it out, it just goes everywhere. Both oil and natural gas are less dense than water, so of course they'll be on top of water. Water will be here at the bottom of the reservoir rock. The reservoir rock is the porous and/or permeable rock that holds liquid deposits. When cap rocks are disturbed, either naturally or through earthquakes, it can happen, naturally, such as an earthquake or drilling. The fluid's going to migrate if it's allowed to migrate. And it's pretty easy to allow it to migrate. In addition to having low relative density, oil and natural gas are often under pressure. So once it's been disturbed, that pressure head may be above the surface of the earth. It will rapidly mobilize. Okay? So lowest pressure, earth surface, that's the classic gusher. That's like an artesian well. The pressure head's above the surface of the earth. Everything comes gushing upwards. We don't see these a lot anymore because we've exploited most of our oil. That's why we have to do things like hydrofrack and look for oil in the tar sands of Alberta. A little bit of history. Where oil is plentiful, such as in the Middle East, it emerges from the ground in seeps. It's still that way these days. The La Brea tar pit in LA is a type of oil seep. It's a tourist trap oil seep. In the past, oil has been readily available to people in this manner. So, throughout history, human beings have used asphalt. These are thick oil deposits. There's evidence that the Neanderthals and Cro-Magnons used them to glue their spear points to their spears. Okay? Evidence for that. Guys ready to go hunting. Use of petroleum is also seen in archaeological fields. Okay? On the banks of the Euphrates River 6,000 years ago, we found asphalt used as mortar and decoration. That relief over there on the left, the black is oil, some form of petroleum. This right here is mortar. Bitumen was used around 4000 BC in Mesopotamia to caulk buildings, and it was also used in the pyramids in ancient Egypt. So that's pretty much all it was used for. People didn't really know that you could burn their stuff. If they did, it was very localized. Despite some early use, oil wasn't widely used. It's been sealant, building material, paint, or as medicine. Native Americans used to ingest it from seeds as medicine, and then it caught on to the settlers in the 19th century, and you had snake oil, like this. Not snake oil, petroleum oil. Good for you. Not really. Anyway, in 1849, a Canadian geologist named Abraham Getzner distilled crude oil and created kerosene. It's one of the first refined distilled products created from crude oil. And he became known as the father of the petroleum industry, although he saw no money and no fame in his lifetime. The fact that petroleum products are readily combustible was key to the way things would turn out. Okay, so this was combustion. Now you were using this as a combustible product. Before this, lamp oil was whale oil. This saved a lot of whales' lives. A few years later, in 1859, the first ever oil rig was created. Pennsylvania Rock Oil Company hired Edwin L. Drake to drill a well near Titusville, Pennsylvania. And I think it gushed, actually. And they were extracting crude oil for lighting oil. The first oil well ever.
Where? Pennsylvania?
Pennsylvania, Titusville. I think it's like, if I recall correctly, it's like middle south. Kind of where the Marcellus is now. The oil industry truly began with the inception of John D. Rockefeller's Standard Oil of Ohio in 1870. In 1901, the first Texas gusher named the Spindletop came into being. And 2 years later, Henry Ford began mass producing the Model T. That was truly the beginning right there, because that's where oil was needed on a large scale basis. And it was a little used byproduct. Up until then, it was practically useless. Gasoline that acted as the energy source for the Model T. Okay. Well, the Model T took off like a rocket, and it drove up oil production. And basically, here we are today. The reason for the use of gasoline in automobiles was due to its relative efficiency. Okay? Gasoline, sort of like a lot of other petroleum products, has a high amount of energy per unit mass, much greater than a lot of other resources. So here's the energy content. So for instance, the petroleum products that we use today is gasoline. You probably used it to get here unless you walked. You took Marty, you still used it. You might use natural gas, actually. 44 kilojoules per gram of energy. Okay, that's a lot. That's enough to lift about 225 pounds, about 3 feet off the ground. That's pretty good. And that efficiency is why we use this stuff. Natural gas is even more efficient. And it has another benefit. It releases less CO2, which is why they're saying, clean burning natural gas. And all the advertisements for natural gas. The rapid rise of petroleum and use of motor vehicles throughout the 20th century meant that fossil fuel, the whole industry, became one of the forces that shaped our world, basically. Big money, a power play. That's what this stuff is. For each day, for instance, each day in 2012, close to 90,000 barrels of crude oil was produced. So that's close to, given a 55-gallon drum, 2 billion gallons per year of oil. Okay. It's still basically that way today, 2013. Okay, 100 years ago, locating oil and gas was something of a gamble. You did what's called wildcat. You knew that there was oil there. Somebody found the sea, Somebody's drilled a well next to you. Your company had the land. You went in and you just drilled. You drilled and drilled and drilled. And, you know, there's a rough estimate, it was a rough kind of life. It's still a rough life. But nowadays, you use geophysics to understand what's below the subsurface. Geophysics utilizes energy signals. Seismic, magnetic, even gravity, often electricity, resistivity, to understand what's in the Earth's interior. It's very, very cost effective. It's extremely expensive to wildcat wells. Doesn't make any sense. Once this crude oil is extracted, pumped, it has to be refined. Once it's refined, about half of it goes to gasoline production. A lot of it goes to jet fuel. A lot of it goes to diesel, but there's a good chunk of it that goes to other products. That could be over 6,000 products. There's oil in this room right now. Then there's peak oil. Okay. Because extraction was so rapid, because it's pretty obvious, if you know anything about geology, we all do, that these resources are finite. They're not going to keep replenishing themselves because they replenish themselves on the order of geologic time, which is not our lifetime. It's not even twice our lifetime. Okay? So, a geologist named M. King Hubbard, he's actually a geophysicist, came up with a way to understand the finiteness of a given oil field and how the volume of production would follow once it reached its maximum. It's a bell-shaped curve, it's a Gaussian curve. Okay? It's the maximum half the oil produced, and there's a steady decline. Now, people think, okay, he meant this to be the decline of oil in the world, but actually it was much more localized. He was just talking about specific fields. That's what M. King Hubbard did. He wasn't talking about the entire planet. That's kind of a fallacy. A lot of people come to and say, "Oh, well, peak oil, Hubbard, he came up with it, and we're doomed." Well, he wasn't really thinking of it that way. Science also often has to be very specific. It's not often, I'm going to come up with a theory of the world or everything. Okay? Although oil and gas, well, sometimes, if you're a physicist, the rest of us have to stick our noses into it. Although oil and gas are non-renewable resources, these are finite resources in volume and extent, there's a resurgence of discovery right now. Because we have unconventional petroleum resources. We have things like the tar sands of Alberta. These are literally sands that contain a lot of petroleum products or unrefined petroleum products. We also have oil shale. Oil shale is a sedimentary rock. Remember I said shale was the top sedimentary rock in the Earth's crust? Well, this shale, contains kerogen. Remember, kerogen is the precursor to petroleum and natural gas, too. Okay, geological and geophysical investigations have revealed petroleum sources in rocks that are much less permeable than the ones we were used to in the early part of the 20th century. Okay, pretty much gone are the very permeable sandstones where you just drill, get below a piezometric surface, or sort of a water table for oil, and just extract. That's kind of gone. You might see that in Saudi Arabia and other places, but that's gone now. Now you have to look for it in rocks that have tighter pore structures, that are basically non-porous, and you have to somehow make them porous. And you do that through fracturing. Fracking is a colloquial term for hydraulic fracturing. It's simply the fracturing of rocks using high-pressure fluids. That's all it is. Send them down there under high pressure, they pop open the rocks. There's a wide range of earth materials of interest that can be extracted using hydraulic fracturing. It's not just oil. Water, even uranium ore particles, is extracted in this manner. But recently, hydraulic fracturing has mainly focused on oil shale and the development of oil shales throughout the world, and in particular interest to us in our own backyard. Hydraulic fracturing isn't totally brand new. It was attempted experimentally in 1947. And in fact, it was in theory and sort of halfway attempted to be done in the early 1900s, but none of that counts because it was very unsuccessful. This was successful as far as the procedure went. They didn't really get a lot out of it. They used 1,000 gallons of gasoline and sand mixture. Okay. So they used a slurry. They sent a slurry down. The experiment wasn't very successful, but 2 years later, Halliburton, you might have heard of Halliburton, okay? It was an oil field service company before it became, something else. Performed the first 2 commercial operations in Texas and Oklahoma, and those were successful. And fracturing became more successful very quickly. The technique was more or less perfected. This fracturing, okay, what's the process? The process is you have specialized machinery that pumps the fluid directly into well bores, or wells that have already been drilled. Okay, you pump them into rock formations where you have done some math, you've done some geologic investigations to figure where there might be differential surfaces. Okay, the differential surfaces are going to be planes of parting. It's sort of like when you're in geology class and you're splitting open rocks. It's kind of like that. And when you know those are there, you send the fluids down, you pop open the rocks, and you send the proppant down after that. The proppant is a porous, permeable mixture, often sand or aluminum oxide particle, placed in the fractures, and it allows for extra permeability. Finally, the rock is permeable, and you can start pumping the rock for the oil, which has hopefully been released. The increased porosity allows drilling operations to extract oil from previously unrecoverable sources, oil shale in particular. Encouraged production is huge. It's become a big industry. Hydraulic fracturing sites are often large-scale operations. They can employ hundreds of specialists. They operate 24 hours a day, 7 days a week, 365 days a year. Constantly operating. You've got your mud loggers, you've got your roughnecks, you've got your tool pushers, all those kind of people operating these machinery. You've got trucks, you've got drivers, and it's constantly going. And when I say it's in our backyard, it's in our backyard. The Marcellus is clearly the largest these days. Okay? This was previously depleted. Nobody thought, okay, we're going to go back to Pennsylvania and New York and Ohio and obtain oil. And Standard Oil of Ohio was named Standard Oil of Ohio because they had oil wells there at one point. So now it's back, but it's fractured. Fracking the shale that's down below. And these are named after what are they named after? The formation. The Marcellus is a formation. It's a unit of shale that extends all throughout this area, under that area. Here in Georgia, we have the Conasauga. There's an actual unit of shale that bears oil called the Conasauga. It's not in operation now. I've looked this up. It's interesting. Now you find ads online for investors. They want people to invest in the Conasauga, the Warrior, the Floyd, from Georgia, Tennessee, Georgia, Mississippi, Alabama, Mississippi, all throughout there's potential oil, and it's going to be developed. It's going to go into operation soon, probably large scale. But right now, if they're looking for investors, because the big money's here. The oil shale is here. The production is here.
Why? Because there's more shale there? Or?
Yeah, there's more. There's just a lot more. So once that gets depleted, they're going to go, well, we better deal with this. Unless an investor or a group of investors comes along, that might start seeing production earlier. But so there's dozens of shale plays in the United States right now. You have the Bakken up there, North Dakota, Eagle Ford, Texas. Okay, play, and what do I mean by play? Well, play is a series of productive oil fields that are all tied to an area and its geology. That's all it is. The plays that occur in the Marcellus play. Because the Marcellus is all one type of geology. Okay? Oil output has increased in 30% since 2008 in this country. Gas production has increased by a third since 2005. This overall increase is seen in development of economies on local, national, and international levels. These oil shale plays have added to a sort of boom, a sort of economic boom in certain areas of our country. The use of hydraulic fracturing has ensured a more secure supply of oil, okay, for energy. It's also provided for thousands of jobs. So these are some of the benefits. There's controversy, too. Controversy surrounds the use of oil, fracking for oil, ever since it began on a large scale. A lot of it has to do with possible environmental and health impacts, okay? People thought extracting this oil, natural gas, they're using chemicals, there is a water table there, there's water. So, oddly enough, there may be two environmental benefits, though. Okay? If you're obtaining natural gas, just natural gas, I'm not talking about petroleum or crude oil or anything, we're talking about the gas. Okay? Natural gas burns cleaner, and it has reduced greenhouse emissions. Okay? It does. Not by much, but it's cleaner than coal. There are some proven impacts, though, to the environment and possibly to human health. Okay? First of all, 99% of most fracturing fluids is composed of water with maybe a little bit of sand. But that other 1% or so is comprised of fairly toxic chemicals. Things like corrosion inhibitors, acid, iron control. If you control your iron, you got some sort of redox reaction going on, okay? Biocide. That doesn't sound very safe. So that's going on too. And these are mostly lubricants. Okay, the gelatin itself is a petroleum product. Okay? These are lubricants that send down there. And some of these actually, there are microorganisms that live in oil. And you do want to get rid of some of them. And I think that's what the biocide is. It eliminates some of these bacteria that feed off of crude oil. Although efforts are taken to mitigate risks, the high mobility of certain fluids coupled with uncertainty of fracture formation poses risk. Now, the geologists who develop shale oil plays, they study these oils and these shales, and they come up with tensor equations to sort of map the fracture fields. Okay, and they're fairly accurate, but there's an element of uncertainty to all of this, and within that uncertainty, that statistical uncertainty, you can potentially be led to a disaster. One bit of uncertainty, a fracture that crosses a municipal groundwater source, and you have a disaster. Because the methane will sort of wreak havoc with your water. It won't mix with it, but it'll mobilize through the water. And there are pictures online of people opening up their taps and setting them on fire.
So that might be one of the reasons why they don't do a lot of fracking in the United States because of the health risk.
Yes, and there's resistance to it too. There's a lot of resistance, a lot of local communities who are just actually opposed to it. Yeah, very much so, especially in Pennsylvania and New York. I mean, there are covenants. People have in their communities, they come up with covenants against this in New York State. There have been reports of methane contamination in groundwater. This is proven. I mean, it's been tested. It's been found. It's true. Okay, it's not, it might happen, let's hug a tree. It's actually happened. Highly mobile and volatile methane is hard to contain. Remember, methane is a very light gas, highly mobile. Once it escapes, it goes every which way, especially under the surface of the earth. Even so, methane has been known to contaminate wells without the presence of fracturing operations. Okay, so it occurs naturally. If you're fracturing, you're going to see an increase in currents of that. So again, you're dealing with statistics. Since fracturing utilizes rapid kinetic movement and pressure changes, now this is something that I think is happening right now. I mean, the pressure changes. Okay, aquifers can be disturbed and released. Toxic materials at the bottom of aquifers can be disturbed. Okay, so a lot of heavy materials, heavy minerals that deposit at the bottom of porous units containing water. And as long as you don't disturb them, they don't get into the water. Well, once you disturb them through hydraulic fracturing, which is an intense kinetic action, it's an intense kinetic motion, okay, then you'll stir these things up. These things will mobilize. They'll go into their constituents. Their ionic constituents may even bond with water. And once you draw up that water in your well, hopefully not a municipal well, you'll have some heavy toxic minerals. You'll have rare earth elements. Arsenic. Arsenic contaminates wells all over the world. It's a problem.
Now they can contaminate the groundwater without even fracturing, right? You saying that's first paragraph?
Oh, well, okay. So there's naturally methane does occur in groundwater. It happens. But what I'm saying is, thinking statistically, you're going to see an increased occurrence of this if you are doing fracturing operations. Yeah. And a lot of this has to be statistical because you're dealing with risk. Okay. Fracking can also potentially affect surface water. Okay, groundwater and surface water, guess what, are not separate. They're topic. They're part of the same system. Okay? A spring is just a surface expression of the water table. Okay. The surface of continually flowing streams and rivers is top of an aquifer, the water table. So they're connected. And once you contaminate the groundwater, you're going to contaminate your surface water. All right? In addition to this, now this right here is very provocative, and I think this is completely true. If you study earthquakes, you realize that when you disturb existent fractures by creating new fractures, you are leading to an activated fracture or fault system. Now, this occurs in nature all the time. Fractures and faults are activated by other fractures and faults. It's a domino effect, and it's because you have kinetic motion. Kinetic motion kinematically activates other fractures and fault systems. So if you're sending down high-pressure fluids into some rock units adjacent to faults, and there's a tremendous amount of kinetic energy going down there and pressure release, couldn't you activate a fault? I think you can. And I think that might be happening. These are all things these are possible impacts that have a lot, there's a lot of credence to these possible impacts, okay? The ones that were before this actually have occurred. They're real. Current legislation in the United States, okay? Is there any? Well, since hydraulic fracturing is a fairly new practice, it's in its inception, there aren't a lot of laws on the books that specifically target it. States have different laws and environmental regulations concerning such industries. Colorado has a pretty terse set of laws concerning this kind of exploration, but it's Colorado, it's out west. A lot of the western states are equipped to deal with this. The eastern states are no longer that equipped because we just don't think of ourselves as oil states. Most states have an oil and gas commission that deals with issues related to oil and gas development. Okay. So right now it's a state-by-state thing. Although there are some federal laws that cover it to a certain extent. The Clean Water Act and the Safe Drinking Water Act cover it in a non-specific manner. Just don't contaminate the water, but they don't target hydraulic fracturing. There's not a lot of legislation out there right now. As hydraulic fracturing continues, okay, we need to continue to study. We need to continue to test for the impacts. We need to continue gathering more data and coming to some solid sound scientific conclusions. Okay? Because on one end, it has proven beneficial to the economy and fossil fuel supplies. We're seeing the benefits economically and as far as fossil fuel goes, with fossil fuel security, petroleum security. But there are risks, and regardless of those benefits, the impact on the environment and human life can't be ignored at all. Okay? As we continue to gather data, we need to come up with legislation. We need to come up with legislation based on the scientific data and the evidence and the conclusions that we come to regarding possible detrimental effects. I don't think, on one hand, you don't want to get rid of the industry. It's proving beneficial. On the other hand, there needs to be some form of regulation, an increased form of regulation. When you let something go, you let something go. And it's hard to get it back. Here's my citations. I've read all of these. I usually read law journals. So I had to read a law journal. There's a lot of legal literature out there. A lot of people doing their legal master's degrees or whatever you do in law on this because there's a need for legislation. And do you have any questions? Thank you.
Can we go back to the citation?
Yes. Oh, absolutely. Any questions? Yes.
So this must be pretty active research on geology. The geology departments are not related to oil companies.
Yeah, well, there are a few, but there are a lot of geologists who are employed by oil companies to do this, and they do one kind of research. If you know what I mean? They're there for their company.
Most of the research.
A lot of it is. Yeah, it's like a geophysical data concerning oil companies. It's done, and there are papers written on it. A lot of the conclusions and the data is kept in the files of the companies. And oil companies, a lot of times, 40 years. Chevron will release, every 40 years, they'll release a certain amount of data and written work.
But are there federal agencies that have, in other words, that they have to satisfy, like Environmental Protection Agency or something?
The EPA, the EPA covers the, Clean Water Act, the Safe Drinking Water Act, and so, and CERCLA, the Superfund too, covers this to a certain extent, but there's sort of a viewpoint in the fracking industry. It's sort of like the Wild West. There's a level of very low legislation going on, and there's a lot of cowboy behavior out there. They're just getting out there, and they see, a company sees that, well, we can just do whatever, and they do whatever. This is why you have communities in New York State coming up with covenants, battling it. Yeah, they're like, no, and they're very active. A lot, and these aren't people who are, they're going to go out and, wear tie-dyes and, do Greenpeace. They're people with houses and families, and they see a risk that they don't want to have. They don't want to have that risk in their backyards. Yes.
Can you shed light about the controversial oil pipe from Canada to Texas? Why?
Oh, the Keystone?
Why it has to be done in Nebraska, but find in Nebraska or North Dakota? Why it has to be taken all the way to Texas?
Yeah. I don't know if that has much to do with hydraulic fracturing. I'm certain that perhaps some of that oil that's going to go through the pipeline originates as fracked oil. That's just a mechanism for transporting the oil that's somewhat invasive, perhaps. Yes.
There's a question online.
Oh, great. Thank you.
Let's see. What are the main causes for the microorganisms developing into petroleum, which is a liquid, versus natural gas, which is a gas? Are there varying pressures?
Well, the thing is, person online,
Myron.
who?
Myron?
Hi, Myron. Thanks for the good question, by the way. Life exists down to 2 miles under the surface of the earth and even below. I mean, we found bacteria, all sorts of things. There's even, a type of worm that lives 2 miles down. So life is really adaptable. And there are types of microorganisms, or types of, one of the domains of life is archaea. Archaea are known as extremophiles. Extremophiles are organisms, are bacterial-like organisms that can exist in boiling water, in hypersaline solution. They're like bacteria, except they occupy their own domain because they are chemically very distinct, biochemically very distinct from bacteria. In fact, archaea are closer biochemically to us than we are to bacteria. So these extremophiles live deep under the earth, they thrive there, and some of them happen to eat crude oil. That's their food. We've used these type of bacteria to, like during the Deepwater Horizon oil spill that happened in the Gulf a few years back, those bacteria were sent in to actually consume the oil that was spilled. So these organisms occur naturally. They're just there. I hope that answers your question.
Well, he did say something about varying pressures. You would find them in the liquid, but not so much in the gas.
Well, yeah, the gas is they can't eat the gas. The gas is the gas, but the liquid is of a sufficient viscosity to where they can munch on it. Mm-hmm. They can derive sustenance. There are organisms that do this. There is life that exists deep under the earth.
I'm sorry, I got it. So what is your name?
Steve Fitzpatrick.
Do you have another quick question? I mean, I was wondering, when they do the fracking, they're taking more substance out of the ground than they're putting in, right?
Yeah.
I mean, wouldn't that eventually lead to sinkholes and
it could.
things like that?
Yeah, that's a good question. If you have rock that is, especially in sedimentary, bedrock, if you have regions that are compromised, you have maybe interbedded limestone. Sinkholes are generally limestone. Limestone is very basic, and it, quote unquote, titrates with the acids in natural waters, and that's how sinkhole, there are a few other conditions. It has to kind of soak into natural plant life, but if the shale occurs with, interbedded with limestone, yeah, sure, absolutely, because when you send these high-pressure fluids down, you pop open the rocks, you create a kinematic situation where you're going to activate things that could pop open again or fall. I mean, it's constrained to a certain, using the tensor equations, they've figured out how to predict how it'll fracture, but there's an element of uncertainty to it, and that element of uncertainty can lead to bad things. Any more questions?
Okay, no more questions. Well, let's thank our speaker for a great talk.
Y'all learned something. I learned a lot. I'm not a petroleum geologist. I learned a lot.
Is your presentation recorded online at all?
Yes, I'm recording it right now, and I will send out the link to all the student chatting once, it's converted and things like that. So I'll send out an announcement.
Are you a DPC or not?
I'm not a professor.
You're